My name is Steve Boggs. I'm the chair of the physics department here at UC Berkeley. On behalf of myself and Imke de Potter, who's the chair of the astronomy department, we are delighted to welcome everyone to this campus tradition. The Regents Lectureship Program has been running for over 50 years, and it brings to the university distinguished speakers who have pursued careers in arts, letters, sciences, and business outside the academic profession. This year, I'm delighted to introduce one of our alumni, Dr. John Mather. John received his bachelor's degree from Swarthmore College in 1968 and came to Berkeley physics as a graduate student. He worked with Professor Paul Richards and received his PhD from Berkeley in 1974. Paul, who is seated in the front row here today, must be acknowledged for educating and mentoring an incredible lineage of accomplished astrophysicists. It's thanks to Paul's efforts that we have John here today as a Regents lecturer, and please join me in thanking Paul Richards for his efforts in this. Great, thank you, Paul. John Mather joined NASA Goddard Space Flight Center in Greenbelt, Maryland, to head as project scientist the Cosmic Background Explorer Mission, or COBE as it is popularly known. He has been a Goddard Fellow since 1994 and currently serves as senior project scientist and chair of the science working group of the James Webb Space Telescope. John received the Nobel Prize in Physics in 2006, along with Berkeley faculty member George Smoot, for discovery of the blackbody form and anisotropy of the cosmic microwave background radiation. Their work on COBE provided exquisite confirmation of fundamental predictions of the Big Bang Theory and laid the groundwork for today's generation of telescopes performing high-precision cosmology through detailed studies of cosmic microwave background. In 2007, John was named by Time magazine as one of the 100 most influential people in the world. Congratulations. In 2012, Time named him as one of the 25 most influential people in space. And that's even more remarkable because, as far as I know, he wasn't even in space at the time. John is a member of the American Academy of Arts and Sciences, the National Academy of Sciences, and a fellow of the American Physical Society. Besides the Nobel Prize, he's won numerous other awards, including the Gruber Prize in Cosmology and the Benjamin Franklin Medal. Please join me in welcoming back to Berkeley, Dr. John Mather.
My goodness. Well, thank you for inviting me to come. Thank you for the lovely reminder of all the things that have happened to me. They don't all feel like they're exactly me, all those awards. I certainly was glad not to be in space when I was awarded that particular recognition, as there's no air up there. So I wanted to tell you a story of the universe and something of my participation in it. So I've called it From Berkeley to NASA, Stockholm, and the Beginning of the Universe. And as Paul pointed out to me, this is in backwards order in some regards. Should start at the beginning. But I would like to start myself with a few thank yous, and particularly to Paul, who's just mentioned. He was my thesis advisor, and his wife Audrey, who was an emotional advisor. Because among other things, when I was extremely discouraged and thought I was all thumbs in the lab, which was, I'm sure, true, Audrey made sure that I got a few words of encouragement. The Hertz Foundation, I thank them because they gave me a fellowship while I was in Paul's lab, and so I was free to avoid my responsibilities as a teaching assistant. And maybe that was a good thing, maybe not. But at any rate, I certainly enjoyed having their fellowship. And thanks to my hosts here for the Regents lecture, which has certainly been a wonderful, wonderful adventure for me to come back and feel the force of being back in Berkeley. I'd like to thank also the huge teams of scientists and engineers who built the COBE satellite and are building the James Webb Space Telescope. And lastly, but definitely not least, the citizens of the United States who are paying for all of this stuff that NASA does. So thank you, citizens. So I'd like to start also with one of the more important presidents that we had, Thomas Jefferson. This was something he wrote before he was president. He wrote about the laws of nature and of nature's God. And then he wrote, we hold these truths to be self-evident, that all men are created equal, that they are endowed by their Creator with certain unalienable rights, that among these are life, liberty, and the pursuit of happiness. So this is a challenge for us who think we are scientists, because there's a big jump between the first 2 lines and the last 4 lines. And so if we ever get to where we think we understand that, we will have accomplished a lot. So I like to think that I'm working on some of the easy parts. You think cosmology is hard, well, the rest of the hard parts are harder. So anyway, another thing to mention about him is he was the president who was very, very excited about science, and he funded the first federal research program, the Lewis and Clark Adventure, which was way over budget and schedule, and was extremely dangerous. And not all of the results got published. But anyway, that was then. So a few stories about some other heroes of science I want to tell you, because I want to put my particular work in some context. This is Albert Michelson. I believe he's the first American Nobel Prize winner in physics. A brilliant experimenter, and I have used his ideas in my thesis work with Paul and since then many times. And he is the person who with Morley showed that the ether must not exist, or at least the ether that we thought about in those days. And just to illustrate how good experimenters are at predicting the future, I have a quote that is attributed to him, although it's not 100% certain. The more important fundamental laws and facts of physical reality have all been discovered. Now this is 1895, and they are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. Our future discoveries must be looked for in the 6th place of decimals. And this was after he had already demonstrated that relativity was going to be required to explain the failure of the ether theory, long before quantum mechanics, real relativity theory, radioactivity, nuclear reactions, cosmology, all those things. So don't take my word for it about what's going to happen next. A few other people in history. This was Schrödinger in 1925. He told us that waves are particles and particles are waves. And we still don't quite understand that yet. We know how to calculate it, but we still don't like it, even though we use it all the time. And everything that I'm showing to you is using quantum mechanics. This electronic stuff is 100% quantum mechanics. In 1926, Robert Goddard, in the middle there, flew a liquid-fueled rocket, the first one based on liquid fuel that I know of anyway, first American one. And the New York Times pronounced that it was impossible to work. So don't all believe everything you read in the papers either. On the right-hand side, we have Einstein with Georges Lemaitre, who was a MIT PhD physicist as well as a Jesuit scholar, and he applied Einstein's equations of relativity to predict that there should be a Big Bang. And Einstein made a lot of fun of him for that, and definitely didn't agree with it. I won't tell you all the terrible things that were said. By the way, small aside, Lemaitre went to see his big boss, the Pope, and the Pope said, doesn't this Big Bang story agree with the biblical story? And he said no. I should also mention that in 1922, Alexander Friedman had made much the same calculation, but he didn't live to find out that he was right. So a few other people. Here is Edwin Hubble at the telescope, and here is the chart that he made in 1929. Now each of those little dots there is a galaxy that he made a measurement of. So the vertical direction shows the speed of motion of a distant galaxy. Most of them are going away from us. On the horizontal direction, the distance. So 1929, this was the measurement of the expansion rate of the universe, because if you divide the distance by the speed, you get the age of the universe. How long did it take for this pattern to occur? And if you picture a little hand grenade going off in the corner, you should get much the same pattern. Although the problem with that is the universe is probably infinite. So the hand grenade picture is definitely the wrong picture to picture. Nevertheless, 1929, this was front page news to compete with the worldwide economic collapse. So we have something to be proud of in 1929. Other things to show you. Here's a picture of Lyman Spitzer. After we got done fighting a war in 1946, he wrote a report to the Rand Corporation that said if we could build a big telescope in space, we could see wonderful things in astronomy. And he even, I think in that same report, said if we could get a really, really big one, let's find ourselves an asteroid and polish up the surface so it's a good mirror, we would be able to build a big enough one so we could see planets around other stars. So we're still pursuing that dream. We haven't got that far, but we've got at least evidence that there are a lot of planets. Other people to show you, Fred Hoyle in this picture. You see he's on the other side of the car because he's in Britain. He really rebelled against the idea of the Big Bang Theory, and in fact rebelled so much they gave it the name that we still use, the Big Bang Theory. That word has been misleading us all ever since. So he had his version of revenge, and he never did, as far as I know, believe that the expanding universe is what we say it is. So something else that happened in that year of 1946, I turned up. And who knew what I would do? My parents told me that I had had all the doorknobs off in the house by age 3. So they knew something was going to happen. So other things that happened, time went on. In 1948, these two gentlemen, Ralph Alpher and Robert Herman, and the image of George Gamow, and here they're talking about the prediction of the early universe, which said the early universe should be hot, and should be filled with a primordial material which they called the Elam, and they calculated what the temperature of that heat should be today, and they got about 5 degrees above absolute zero, which is remarkably close to the number that we measured of 2.7. So that's a pretty amazing story in itself, considering that we had slide rules for computers. A few years later, something that happened and affected almost everyone shortly. In 1948, this was the picture we had of Mars. 1954. And I was a child. We went down to see the Museum of Natural History in New York. The planetarium show was about Mars and how the canals might be there. So everybody was kind of hopeful that the Great Palomar Telescope would see them, but it didn't. That's because they weren't there. Another amazing event occurred in 1957. The Sputnik went up, and every child in the country was aware of this fact, and every adult was terrified, as far as I can tell, that the Soviet Union could now invade the United States with complete impunity. Although the U.S. had been warned that this would happen, in fact, it had been reported 25 times in the New York Times that this was going to happen, nevertheless, people were pretty worried. So that meant that the United States would now support science and engineering in a way that they had not done before. Science and engineering were big during the war before that, but this was another even more terrifying thing. This was a year when children were taught to hide under the desk in case of nuclear attack. So anyway, we did some good things out of that, and we began to learn a lot of things that you never would have guessed we could know. Now I want to jump into some of the basic science of what we're up to, and maybe this will be a surprise to you. When you look in the mirror in the morning, you are looking at something cosmological, because astronomers will tell you that the atoms we're made of were all produced inside stars and have been recycled out. Not only that, the material may have been expelled all the way from our galaxy out into intergalactic space and fallen back in. So we are completely and totally recycled. So when you're looking in the mirror in the morning, just think of that. Who are you looking at? The insides of stars. Of course, everything else has been recycled too. We are definitely drinking dinosaur piss and breathing dinosaur breath. And our bones are made of the same calcium atoms that theirs were. So that's part of our story, and I'm kidding you a bit, but now I want to also point out that astronomers are the only scientists who honestly do look back in time very far. We look at things as they were when they sent light to us. So when you look at something 1 light year away, you see it as it was 1 year ago. When you look at your hand, you see it as it was 3 nanoseconds ago. If you could look all the way back to the most distant things in the universe we could imagine, almost 15 billion light years back, 15 billion light years out, 15 billion years back in time. So this is really simple. The penalty that we pay for this great pride is that we get a very blurry view. And so you can only do it with telescopes and great calculation and imagination. So now you say, well, maybe I believe that, and let me tell you, how do we measure this? How do we make Hubble's chart? So we start with trigonometry, just as you would have done in high school, just as the Egyptians and Greeks and Indian civilizations would have done thousands of years ago. Draw a triangle. If you have two angles of the triangle and one side of the triangle, you know the entire size of the triangle and shape. So that's surveying, and so we are able to do that in the neighborhood. The Greek astronomers were able to get the distance to the moon, even this way, as well as the diameter of the Earth. And they tried to get the distance of the sun, but that was too hard and they couldn't do it. So the other method that they would have also understood quite well is what we call the standard candle method. If I promise you that those two candles are equal in brightness, and one of them is fainter than the other, then when we look at them from a great distance, we'll say we can use the inverse square law to calculate the ratio of distances. So this is how we survey the universe. And it works really well, although it gets pretty tricky, because how do I prove that that's the same as that? So then other thing we can do is we can measure motions. The Doppler shift is the effect that we use, and you can hear it in sound waves quite easily when a train goes by or a motorcycle passes you on the freeway. But if you spread out the sunshine with a prism and do it very well, you get marks across the rainbow that are called spectrum lines, and they come from the atomic and molecular species in the surface of the sun. So now if you look at another star and you see a similar pattern, you say a couple of things. One, the star is similar to the sun. The other is, what if the wavelengths are all shifted by a certain amount, by a certain factor? And we call that the Doppler shift, and we can use it to determine the motion of the distant object. If it's coming toward us, the wavelengths are shorter. Going away from us, the wavelengths are longer. And so now we can measure the expansion of the universe. So this was the technique that Edwin Hubble used to draw that chart. Now, I should mention that the previous method, that what he did when he did this method turned out to be wrong, because that kind of candle wasn't the same as that kind of candle that he was using. So this confused astronomers a great deal for a long time, because after a while we knew that the Earth was older than the universe. Couldn't be. So there was something the matter. You can perhaps excuse Fred Hoyle for his skepticism, considering that the data were pretty wrong. Okay, so this is another cartoon I have to illustrate that although everyone will say, where was that Big Bang? And I told you this wrong story about the firecracker or the grenade. Actually, astronomers have not found the center of the universe. And as far as we can tell, there is not a center of the universe. The center of the universe is that way. It's over there. It's over there. Everything that we are in was in the universe, and it didn't have a center. Now, if there is one, it's too far away to find it. So I can't promise you there is not one, but we cannot find it. So this illustrates what three different astronomers would see each other doing. This one, the human one on the left, says that she can measure the age of her universe, and it's 1 hour. But now imagine what the one in the middle would do. She could also make the same calculation and say her age, her universe is 1 hour old also. But see, there's nobody in space. You can't tell who's standing on the grass. So all of the astronomers throughout the universe will calculate that they feel that they're in the center. So this is the strange and exotic behavior of infinity, that we cannot find the middle end, we cannot find the edge, and there doesn't have to be one. So pretty startling, but seems to be the story that we have. So it also means I can be excused perhaps for not being able to draw a picture of the universe expanding, because you can't. You cannot stand outside the universe and draw a picture of it. So at least not yet. I don't know what new technology would be needed. Also, the Big Bang that we call it is the wrong name, because you cannot help thinking of the firecracker at a place, but that's not what we mean to convey. So Fred Hoyle has had his revenge. Now you could say, well, okay, maybe I believe your story about the expanding universe, but how am I here? Because my universe has never been expanding as far as I can feel. The Earth doesn't expand. It doesn't get any farther to get from here to New York. So how does that work? So we have a story to tell you, and it is that the early universe, although it's expanding, it has gravitation that reaches across immense distances. And in some areas where the density of the early universe is more than average, the gravity can stop the expansion. So material will expand out, and then it will collapse back down in. So this is our story about how come we are here. It's because gravity, operating on the early universe material, is able to stop the expansion. Then after it does that, we can have stars, we can have galaxies, we can have a continuous flow of light from the sun to support the complexity here on Earth. We can have the atoms that I told you were made inside stars that blew up. So we are here because of this one fact, that gravity is a long-range attractive force, and it was able to stop the expansion in certain places. So pretty remarkable story to tell, and I wouldn't tell it to you if I didn't think it was true, but it has made a remarkable progress in cosmology possible. So here's a chart that summarizes the current picture of the history of the universe. We have a snapshot taken with microwave background radiation here. I'll show you more about it later. We have an idea that galaxies form by merging small things to make big things. We have a picture of our nearest neighbor, the Andromeda Nebula here, and you can see it even has two things falling in. I hear a few ripples thinking of sound, of talking about the horrendous space kablooey. That is the name that was given by Calvin in the Calvin and Hobbes comic strip when Sky and Telescope had a contest to rename the Big Bang. So anyway, I like this name better. What's better about this is it does not say, it's like a little firecracker going off in a corner, and you cannot imagine from this name that you can find the middle or the edge. So it's a better map, a better idea rather. So whatever it was, it set up the early conditions of the universe, and it doesn't even say that there was a beginning. Notice almost every popular story you'll read about the early universe, they will say the universe began. Well, as though it sprang into being from nothing. We don't know that. As far as we can tell, all we know is it's been changing from one thing into another. So philosophers and others should point out that it doesn't have to have a beginning. It can be expanding. Just the fact that the clock hasn't ticked more than 13.7 billion years doesn't mean that there was a time before time. Doesn't mean that there was time zero. Anyway, so we have this story, the early universe. When the universe is about 3 minutes old, the atomic nuclei of helium are made. When it's about 389,000 years old, the electrons latch onto the atomic nuclei, and suddenly the early universe becomes transparent. This is a very important point because at that time, the heat radiation that's there at that moment, suddenly becomes free to travel through the entire universe, and we can then take its picture with microwave radiation. So that's what we did with the COBE satellite. So then we have hypothetical events here on this story, because this part has not been observed. We imagine that the first generations of stars were very different from the ones we have today, and that they blew up very quickly to make the first chemical elements and also some of the first black holes. So then the rest of this I will skip over until later, but that's what we might have for the early history of the universe. So another few pictures of history of us. Here is the document from the Congress creating NASA. So why do I care about NASA? This because I work there. 1958, this was NASA, the federal response to the fact of the Sputnik. So we now had to go into space and do things, and only 4 years later, let's see if this works, President Kennedy went to Rice University and he gave a talk in which he announced that we were going to the moon. Can you imagine only 4 years before you take on this extraordinary challenge? Let's see if it'll play here for us.
But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
That was an amazing thing to happen. Now I want to show you a picture of another man who made it possible. This is James E. Webb, the man who we name our telescope after today. He was the one who figured out at NASA how to do that, how to get people to the moon in a decade. And we did it. He was a master manager, he was a master politician, he understood politics, and he understood people like me enough to not believe people like me. He doubled the budget that he was going to request in the taxi cab on the way to see the president. And if he hadn't done that, it would have been a national disaster and total failure. And so we owe a lot to that man. Not just for that, but also because he said, we need to have science, and he made sure that we went to the planets. We went off to Mars. We went out of the solar system with the things that he sponsored. And he started, as I understand it, laboratories like the Space Science Lab right up on the hill, because he went to the president and said, we need to have this have a lasting legacy. This should not just be a foreign policy adventure. So that was James Webb. So now back to my story a little bit. This is me in graduate school. This is the little house on Walnut Street behind the university garage where I used to live. This is LeConte, where I spent most of my life, it seemed like. I came here in 1968 from college, intending to go to Princeton University for graduate school, but I got a summer job up on the hill at Lawrence Berkeley Lab, and I switched my opinion. So I decided to stay, and I was permitted to stay, and I wanted to be like the famous physicist Richard Feynman, because that would have been so cool. But after a little while, I found out that was pretty hard. He was Feynman. What happened to my voice? Okay, he was already Richard Feynman. People told me there are no jobs for theoretical physicists, so I went around talking with faculty members, what shall I do? And I found Paul Richards, and I thought, oh, well, I really like his idea. And he was working with Charles Towns and Mike Werner, who were going to measure the cosmic background radiation from the ground. And I didn't know yet that Paul would be thinking up other things to do, but eventually we started up projects. I worked with David Woody, another grad student, and Norm Nishioka and Rick Auerbach here in LeConte to build a payload. So what else was happening in 1970? In 1970, people used vacuum tubes. Some of you have never seen one, but it was a very big deal. Something we call the fast Fourier transform, which is now the basis of almost all telecommunications, among other things, had just been invented. This is just an algorithm which changed everything. Pocket calculators did not yet exist. They were invented and built right back then. The advanced laboratory computer used paper tape to record the programs, and we made our infrared detectors with a soldering iron and a little saw. So here are some of the people. This is me, looking very, very hairy. There is Paul. I'm sure the picture is a little too white here to see all of his features. And there's my lab partner, Mike Werner, who has gone on to become, among other things, the project scientist for the Spitzer Space Telescope. So here's our lab. Paul gave me this picture this week. There's David Woody, and here we are with our balloon payload, which we launched in 1973. We drove down, David Woody and I drove down to Texas with a university truck, totally loaded down with equipment. Eventually, Paul came down, and people from the Space Science Lab, like Henry Primsch, came down, and we flew our balloon payload, and you know what? It did not work. So Paul graciously allowed me to write a thesis about the ground-based experiment that did work and the design of the thing that did not work. And afterwards, David figured out the reason why it didn't work, and it was fixed and flew perfectly the next time. Meanwhile, I had escaped to New York City, thinking that this subject was much too difficult. I was never going to do that again. So I got a job as a postdoc above Tom's Restaurant, which you might know from Seinfeld. And the Goddard Institute for Space Studies, which is a NASA laboratory, is this building here. So I worked there, and I ate every day at Tom's Restaurant. And so maybe the food was good, enough to make good things happen. At any rate, I bicycled to work, and while I was there, NASA said they'd like to have proposals for new satellite missions. So this was just 5 years after the first moon landing, and so I said to my advisor, well, you know, my thesis project didn't work, but it would have been better if it could have been done in outer space. So he said, we will write a proposal. And we wrote one and sent it in, and NASA said, okay, although it took them a long time to do that. So now I want to put you back in 1985, which is after that moment, but before the product was launched that we had proposed. See, what were people thinking about in 1985? So this was a year in which NASA needed to explain to the Congress why they needed to build 4 telescopes. Not just 1, 4 telescopes, all of which were huge engineering projects. And so here it is. How did the universe begin? So there's that misstatement already. We already were saying the universe began, and I don't think that's the right word for it. Would we find new laws of physics that govern cosmic evolution? So in 1985, we didn't know yet about the cosmic dark energy, although it had been guessed at. The cosmic dark matter, we had measurements that suggested it. We certainly didn't know about cosmic inflation yet. We believed that galaxies formed very differently from the way they did, but anyway, we wanted to know. How are the stars born? We certainly know in general terms, but in specific, we still do not. How did life start? How are the planets formed? All these things are wide open topics in 1985. We have made progress on all of them, but the subject is not done. So NASA needed to build an infrared observatory, a visible ultraviolet observatory, which was the Hubble telescope, an X-ray observatory, which is called the Chandra, and a gamma ray observatory called the Compton Gamma Ray Observatory. And they built all 4 of them, and they all worked. And we learned amazing and wonderful things and started new generations of astronomers into the world. A little more astronomy. Here is a picture taken by the Hubble Space Telescope. I don't know if we can lower the lights at all so you can see this even better. But what the picture shows is the result of pointing the telescope in one direction for 2 weeks and just waiting for the photons to come in. And the direction was originally chosen because there was nothing there to look at that people knew about. So some people thought, what a waste of time that will be. Other people said, what a wonderful discovery we might make. And so what they found was the galaxies are far more numerous than they had imagined, and that there are many, many thousands of galaxies in this one picture, and many of them are very faint and very far away. And that was very big news because that was counter to the predictions that very famous astrophysicists had confidently made about how the galaxies formed. So another very important fact about this picture is it says even the great Hubble telescope cannot see far enough to see the formation of the first galaxies. So even the wonders of that magnificent observatory, which has been upgraded 5 times, still not quite enough to answer every question. I don't think you should be surprised. Another picture, this is a picture of a nearby galaxy like our own, 100 billion stars more or less rotating around a common center held together by gravity. So if our sun were in this galaxy, it would be somewhere out here on the edge. Because we're definitely not in the middle of our own. Anyway, we would like to know how this works. We would like to know how the sun and the solar system came to exist. And so we get to do it in part by looking at other galaxies to see how they work. I told you earlier on that we believe that stars explode and the material comes back into space. Here's one which human beings observed. In 1054, this star exploded and it was so bright you could see it in the daytime. And we know when it happened because it was written down by Chinese astronomers, and we still even have records of that. So the story I told you about stars exploding is not just, quote, a theory. We saw it happen. So how do stars form? Well, we have pictures of this amazing part of the Orion Nebula, and on this picture you cannot really tell all that well what it is, but there are many hundreds and thousands of stars in this cloud of dust and gas, and it's beautiful to look at, it's magnificent, and it tells you that you can't see what you want to see. And the trouble with, what do we want to see? Well, we want to be impressed by beauty, but we also want to know how does it work? And so there are stars being born in these clouds, which are completely hidden from us while they are being born. And they're hidden from us by dirt, dust in space, which absorbs the starlight and just prevents us from seeing in. So some of these really dark spots here, those are places where stars are being born as we speak. So that's part of the story that we fit into. Now I'll jump back to the project that I was working on based on the proposal from New York and NASA. This is what eventually flew 15 years later. It's called the Cosmic Background Explorer Satellite. And so what it contains up here are 3 instrument packages, 3 boxes on the outside here, which had microwave receivers on them, and they made a map of the sky. 2 instruments on the inside cooled down to 1.5 degrees above absolute zero to measure the cosmic heat directly. So the rest of this is protection. This big cone protects the instrument package from the sun and the earth, and this part down here is solar panels and all the stuff that NASA needs to make this part in the top work. So that was launched in November 18th of 1989. And within about 6 weeks, we could make this chart, which we showed to the Astronomical Society in January of 90. And when I showed this chart, which was done with the old plastic view graphs, it got a standing ovation, which completely amazed me, because I knew that was the right answer all along. I actually didn't, but the experimenter must have an open mind and must search for every possible problem. At any rate, what we have here is this theoretical prediction of the Big Bang Theory, even though that's the rotten name for it, is the smooth curve, and the little boxes are all the measurements, and you can see they're all right on the curve. So this was a tremendous relief for all the astronomers, because we had a long time of difficult measurements which suggested the opposite was true, that some of these boxes were not on the curve. In fact, my own thesis project was working in that direction, that this wasn't quite perfect. So it was standing ovation for that one, and eventually my colleagues at NASA decided to shrink the error bars down to 50 parts per million, and it's still the right curve. So this is probably the best measurement of this sort that has ever been done, but it's not the best that could be done. A couple of years later, we got to make this presentation. This is the cover of Physics Today, although the pictures were shown in April of '92. George Smoot got to present these charts because these are measurements of the cosmic bumps. So the one to focus your attention on here is this one at the bottom. It's a map of the entire sky compressed onto an oval. And these blobs, these pink and aqua-colored blobs, are measures of the difference of temperature of the universe from one place to another. So very small differences, a part in 100,000, which is, to me, it's still astonishing to me that we're able to accomplish that with equipment that operates not all the way cold, but at not that far below room temperature. So hundreds of millions of measurements were combined to make this map. So when Stephen Hawking saw this map, he said it was the most important scientific discovery of the century, if not of all time. So again, I was a little surprised by that, because why is that so important? Well, we thought it was just a tremendous accomplishment that we had measured something. So why did he think it was so important? Well, I'll tell you a few things that I've come to appreciate since then. Number one, I told you the story that gravity reaching across tremendous reaches of space would cause certain parts of the universe to stop expanding, to collapse back down to make galaxies and stars. This is that. These are the measurements of the hot and cold, or dense and less dense regions of the early universe, and it's just the right amount for gravity to work on those spots so that galaxies can form and we can exist. So in that personal sense, it's very important, because without that, we wouldn't be here, or at least we wouldn't be able to explain how we are here. So that's pretty important. Another thing that we are now coming to appreciate and still working on is the idea that the early universe came from some kind of quantum fluctuations, and these are quantum noise, quantum fluctuations in the primordial material. So we don't quite know how to interpret that, but that's the idea that we are currently working. So we're observing the quantum mechanics of the early universe by making this map. So this is pretty spectacular. And I think none of us experimenters ever had dreamed how important this would turn out to be when theoretical interpretation continued to work. So a few years later, some of my colleagues at NASA and at Princeton, that's Chuck Bennett and David Wilkinson and others, produced another satellite which made a much, much better map. And although it looks different, it basically says the first one was correct. And not only that, all these tremendous details are extremely important. They're pretty random, but there's a pattern to the randomness which can be analyzed and used to make extremely precise measurements of everything we wanted to know, almost, about the early universe. So this confirmation, I think, was probably essential to the page that I'm about to show you. So in 2006, on I think October 3rd, I got a phone call from Stockholm, and they wanted to know if I was the real John Mather. And they wanted to tell us that they're awarding the prize for our discovery of the black body form, which is the curve with the little boxes on it, and the anisotropy, and not ISO the same, tropy direction, so it's not the same in every direction. The universe has bumps. So that was the call from Stockholm, and my life has been completely different ever since. So immediately got on the phone, and within about 15 minutes, I realized I was never going to have breakfast or a shower if I didn't take the phone off the hook. So anyway, eventually we organized a trip to Stockholm, showed my chart a lot more, got my diploma from the King of Sweden, and eventually a check, which went into a foundation for science and the arts. So now a little more back to some science. A long time ago, astronomers were extremely clear in their minds that gravity working across great distances would slow the entire expansion of the universe. And so we calculated this, and we built the Palomar Observatory to measure this, and it turns out not to be completely true. So yes, indeed, the galaxies do pull on each other, but in 1998, these three folks, among others, figured out that the universe is not just slowing down, it is speeding up. So this is called the accelerating universe, the breakthrough of the year for that year. And in 2011, this discovery received the Nobel Prize. And there's our colleague Saul here, and there's my Baltimore friend Adam Rees and Brian Schmidt working from Australia, all working together and competing to get this answer. So now we know the universe has something called dark energy in it, which means we don't know what it is. As it happens, the measurements fit perfectly with Einstein's number, we call his Einstein's constant, which was disgraced after the discovery of the expanding universe, but has come back in a new form. So maybe Einstein was right more times than he thought. So anyway, so what do we do now? I want to show you a few bits about the new telescope that I'm working on, the James Webb Telescope. So why do we need a new telescope? Well, what did we find from Hubble that you can't learn enough about? So, number one, Hubble told us that the distant galaxies are too redshifted for us to see them all. So, and that's because of the expansion of the universe. Number two, we know that the Earth's atmosphere is opaque enough at infrared wavelengths that we can't see what we would like to see. And number three, we see that the universe is very different when you use an infrared camera. So, we would learn new things and see much farther if we could build ourselves an infrared telescope. So the astronomers wrote books about this, and in fact a lovely report called the HST and Beyond report is an extremely poetic report. If you really want to know why we're doing it, it gives you goosebumps just to think that we could do the things that it says. So this led us into a building of a radically new and different type of telescope, the James Webb Telescope. And here it is. It doesn't look like anything we've ever built before. Here it is, the big giant collector. It sort of looks like a solar energy concentrator, doesn't it? Anyway, the light comes from the distant universe, bounces off this big, almost parabolic mirror into a small mirror, down into the instrument box back here. And what's different about this is this doesn't have a tube around it, it has a big umbrella instead. So here the sun is below, here's the big umbrella, and was that me? Maybe. And so here's the telescope looking out, very different from any other. So who's building it? Goddard Space Flight Center, where I work, is the lead organization in Greenbelt, Maryland. We are in an international partnership with European and Canadian space agencies. And our prime contractor, the place where most of the money goes, is the Northrop Grumman Aerospace Systems just outside LA Airport. So we have instruments coming from around the world, run from Arizona, plus, of course, aerospace contractor Lockheed Martin nearby, near-infrared spectrograph coming from Europe, mid-infrared instrument coming from Europe and Jet Propulsion Lab, and a fine guidance sensor coming from Canada. So that's our basic international team. This telescope is truly gigantic, and I'll show you more about it. This mirror is about 21 feet across, 6.5 meters, so it's like from the stage to the ceiling up here. It's an enormous mirror. It's much bigger than will fit into the rocket, so it's a truly challenging engineering project. I'll show you how we do it. So it's called deployable. That means it unfolds in space. It is going to be very cold. This telescope comes down to about 40 degrees above absolute zero. And the Europeans are buying the rocket, so we will take our telescope down to French Guiana to push the button to launch it into space. It'll eventually have approximately a 10-year life, at least that's the amount of fuel that we are carrying for it. So here is how big it is. This is a steel model that's built for a general display to the public. Here's the telescope. This big umbrella is about as big as a tennis court. So imagine Roger Federer running back and forth on his half. So people are very small. Here's a person down here illustrating this. This model has been traveling the world. It has even last year been to South by Southwest Music Festival, and 15,000 people came by to talk to us about it. So this is a pretty amazingly popular exhibit and attracts a lot of general public support. But how does this work? Here's the telescope as it is in space up here. Side view, there's the instrument box. Here's the big mirror I told you about. Here is the big umbrella, 5 layers as seen from the side. And here's the sun over here, not nearly bright enough, shining up here on the spacecraft. Here it is folded up in the top of the rocket. The rocket is a standard commercial product that built in Europe. So, but we are the origami telescope. Has to be folded up to get in there. We are sending the telescope very far out. It's approximately 4 times the distance to the moon that we go out to do this. Now we'll show you my equivalent of 7 minutes of terror. This is how the telescope has to unfold when it's in space. First, we unfold the solar panels for 2,000 watts of electricity, then a little antenna to send the data back to Earth and receive commands. Now we're beginning to unfold the umbrella, the sun shield. This will take place in the first 2 weeks after launch. Here we're separating the telescope from the warm spacecraft box so it can get colder. We're unrolling the covers that cover up the umbrella. This is all done by remote command. We cannot go out there and fix it. So it's way too far away. No user serviceable parts inside. Now we have some booms coming out. This is all done by cables, motors, gears, pulleys, wheels, all kinds of different actuators. And we have practiced this, so we're pretty sure that it'll work, but we are doing a lot more practice. And the final version will be tested 5 times before we fold it up for the last time. Finally, we deploy the telescope itself, unwrap the wings that have the hexagons on them. So now the mirror is complete. All 18 segments are in place, and it's still not in focus, but at least it's in orbit. So there it is, our magnificent telescope far away from Earth. By this time, it'll be well beyond the distance of the moon by the time it's in this shape. So in principle, if we had a problem, we could go out there with a robot, but we don't have it ready today, that's for sure. So where is this place we're going? It's called the Lagrange point, after Joseph Louis Lagrange, who figured out all 5 of them in 1772. But the one we choose actually was figured out in 1750 by the great physicist, mathematician Euler. So we go out 1,000,000 miles, and here is the not to scale drawing. So I like to remember that this was before we had paved streets in most of the United States. And that he was able to do that, and he could have done it probably in his head, though he probably used a pencil. So the mirrors are an amazing technology we had to develop. When we said we wanted to build this telescope, they said to me that couldn't be done. So what do you do when you can't do it? You offer a competition. So we had contracts, proposers said they knew how to do it. Eventually, one of them was chosen, and they did know how to do it. This is 6 of the big hexagons in the test tank down at Marshall Space Flight Center in Alabama. And by the way, they were all polished in Richmond, California by Tinsley Laboratories, special facility that they made for us to do it. The mirrors are made of the element beryllium, which is extremely light and stiff, and they are coated with element gold, probably one of the less expensive materials that we have, because there's very, very, very little of it in there. Probably the amount in my little ring here would be enough to cover all of those mirrors. At any rate, so we have finished them all. They have all been delivered to Goddard, where I work. And now our next step, eventually with the mirrors, will be to prove that they focus. So in the meantime, we built a scale model telescope with 18 hexagons, and we learned how to focus them after launch. We learned from Hubble. And in fact, the mathematics that we use is exactly the mathematics that was developed for the Hubble repair. I'll illustrate just one of the instruments that we built. This is the European contribution, and it's an extraordinarily complex device. And curiously enough, they decided to make it out of the material silicon carbide, which is a popular material in Europe, especially if you have a BMW, you probably have silicon carbide brake shoes. But at any rate, it's an aerospace material. What it enables us to do is to observe 100 galaxies at a time and get their spectra. So we had to invent a particular thing for this, which is called a micro shutter array. There are 250,000 little tiny shutters that can be opened up to allow the light of the preferred galaxies to come in. Here's a micrograph of some of these shutters. You can see they're about comparable in size to the diameter of a human hair. Nevertheless, we can control all of them from the ground. If you want to see how we're doing with our project, you can watch us. We have web cameras on the James Webb Space Telescope website. So this is, as it was a long time ago, a big empty clean room. This room is now almost completely filled with equipment, and by the time that we're done putting the telescope together, it will reach from floor to ceiling with telescope. But you can watch us work. Usually when you look in there, there are a few people in there with white bunny suits, and they're wearing those to prevent contamination of the equipment. Anyway, the equipment has arrived. All of the mirrors are done, and all of the instruments have arrived, but there's still a lot of work to do. So among other things, we will take the telescope down to Johnson Space Flight Center in Texas. We will put it into an even bigger vacuum tank down there. Here is the telescope at the bottom looking up at the equipment. This is the same vacuum tank that the Apollo astronauts used when they were rehearsing getting out of their space capsule onto the surface of the moon. So it's a historic register site in the National Park Service, but they nevertheless allowed us to use it, and it is truly immense, but it's just the right size. So to wrap up, I'll show you a few of the scientific things people are expecting to try. We have, using computers, simulated what I told you was happening, that gravity acting across great distances of space could pull stuff together. So here is a simulation in a supercomputer of the formation of galaxies. So you see blobs being pulled in and merging together just by gravitational forces. So the picture is actually showing us two kinds of matter. There's ordinary matter, the yellow stuff, and something we call dark matter, which our astronomers are really sure exists. Nobody else has yet seen it. But we're not holding our punches. We are completely convinced this is real because that dark matter has gravity. We see it in so many places. Another thing so anyway, we want to know if that's a true movie. Now the details will not be true, but the generalities might be true, and we have to find out by looking. Here's another thing that's likely to happen. That beautiful Andromeda Nebula that I showed you is coming toward us. And in about 2 billion years, maybe 3 billion years, we will have this occur. In fact, it has just recently been measured whether we're going to get a direct hit or not. And it's pretty near a direct hit. And what happens when galaxies collide, the stars miss each other and they go right flying past each other, but gravity, working across this spaces, will pull it back together again. So we don't know whether whether the solar system is going to be expelled from the Milky Way and go flying off like some of these, well, that's quite possible, or whether the gravity will be enough to pull them all into the inside. Now, by the way, by the time that this happens, it's going to be too hot for us to live here, because the sun is getting brighter, and this is not our fault. But you can see a completely dramatic collision occurring here, and whoever is around in that future time to look at it will have a wonderful spectacle to see. So, very, very complex. What else do we want to look for? We know that nature has given us some extra lenses in our telescope. And this is something Einstein predicted would occur. He was expecting that it would never happen, that no one would ever be able to see it, but he didn't plan on a century of progress. So what we have here is a beautiful picture of hundreds and thousands of galaxies, very massive galaxies. They are capable of bending light. Einstein said gravity could bend light. So sure enough, here is a magnified image of a very, very distant little dot. It should have been a little dot, but it's been stretched out by the gravitational magnification of that light. So nature has given us several hundred of these lenses out in space where we see these magnified images of distant galaxies. So that's one of the things we'll use to look back in time. We will look inside places in the nearby where stars are being formed. One of our most beautiful pictures from Hubble, a place where stars are being born as we speak, it's called the Eagle Nebula. And you say, isn't it beautiful? Well, yes, but astronomer says, but I want to see what's inside. So here is what we try. If you take an infrared picture of the same picture using a big infrared telescope on the ground, you can see through the dust clouds, and inside there's a star that wasn't there on the other picture. So this is our strategy for learning how stars are born as we speak. There's roughly one new star a year being born in the Milky Way, so that's a lot. So we should be able to find some, and if we're really lucky, we'll even notice when one turns on. So another picture to illustrate this, here is a Hubble picture on the left and on the right. They have a little bit of infrared capability. Here's a new star being born. Here it is as seen with the infrared, so we know this story is correct. You can see through the dust and into the inner workings of the star being formed. Something else to try, we will be hunting for planets. We now know there are as many planets as there are stars in the Milky Way, and a few of them have even been seen directly. This one was one of the first. It was seen with the Hubble Space Telescope. Here's the stars in the middle. Here's this ring of dust orbiting around like the Saturn's rings, and it was predicted there should be a planet over there, and sure enough there is. It's a kind of oddball planet because it's too bright for us to explain everything, but anyway, it has been seen, I think, 4 or 5 times now, as we even know its orbit around the center star. We've seen a planet around another star, the first time since Neptune was discovered that we knew where to look, and it was there. We can see some of them from the ground if we do what's called adaptive optics. This blob is actually just a blob of stuff that's not really there. There's a star in there somewhere, but they've seen at least 3 little planets, not so little, orbiting around it. So we can do some work from the ground if we try really hard, but here is another technique which we can do. If we wait for a while and stare at enough stars, sometimes a planet will go in front of the star and it'll make the star dimmer for a while, and that's what we call a transit. And that's a very powerful technique. We have already seen roughly 3,000 such things occur using just the Kepler Observatory. Half an orbit later, the planet will go behind the star, and if the planet was bright enough, you'll notice the combination gets fainter again. So both of these techniques have been demonstrated with Hubble and with Spitzer space telescopes. The advantage for the Webb telescope is that it is so much bigger, we can now study the light that went through the planetary atmosphere on its way to the telescope, and we can get a fairly decent understanding of the chemistry of another planet. So this is a completely spectacular possibility for us. We calculate that if we look at the right one, we should be able to tell if an Earth-like planet has enough water to have an ocean. So not to say that we can tell yet that it's alive, but maybe that it has a chance. So I like to speculate, even though Michelson didn't get it right, about what's coming in the future. And so what is going to come, I mentioned that in the long-term future, things will happen. I guess everybody here is fretting about the next few hundred years that we're going to run out of coal and oil, which is clear enough. And by the way, you know, if you were cursed by the gods in ancient times, you could be made a seer, and you would know the future, and nobody would believe you. I don't want to have that. But about 1 billion years in the future, I told you the sun is getting brighter. It will be too hot for us to live here. In about 5 billion, the sun will become a red giant, roughly the size of the Earth's orbit. And by then, that beautiful collision I showed you will be colliding. In about 7.6 billion, the sun will turn into a white dwarf and start to shrink down to a very small size. And then, if we're still here, if any of our descendants are still around, they'll have to move in closer and closer. Now, what we also claim, and this may or may not be true, because there's not a whole lot you can test this about, the accelerating universe, due to the dark energy, will probably continue. The stars will go out, the black holes will evaporate, and it'll be a cold future universe. Now, some people tell me this is a terrible story to tell because it doesn't continue to infinity. But, you know, 1 billion years is a pretty long time. I don't think we should be fretting too much about that. You could also speculate about how far can we go in space travel. And I guess one thing that seems fairly likely to me is just a very short extrapolation of what we're seeing today. There are robots everywhere. There are robots under the ocean, drilling holes in the bottom to get oil out. We can send robots to the stars, throughout the solar system. I don't know how many robots are out there doing other things. We have robots to do surgery for us. And so robots are getting better all the time, but we're not. We're just as fragile as our ancestors were 100,000 years ago. So if we're going to go traveling very far, we have to work extremely hard at it. And just getting to the moon was tough enough. And we were lucky that the astronauts weren't killed by a solar flare. Getting to Mars is one heck of a more risky deal so far. So what are we going to do? Well, I think these guys, these robots, are going to get better. And we're going to keep on pushing them because zillions of dollars are at stake. So maybe we'll own them and we'll tell them what to do, or maybe they'll get so smart that they'll have an opinion. And if the robots want to go, they will. But just as a reminder, the laws of physics are against getting very far. Space is way too large for a robot, even a robot, to go anywhere but the nearest possible places, because 4 light years is one heck of a long time. So even if a really smart robot wants to go to the next nearest star, they're going to have to take a very long trip. So in practical terms, we're alone here, and we better pay attention. So if you want to know more about all this, there's a paperback book that I did with John Boslow a long time ago, and there are lots of websites where you can hear about it. But I'd like also just commend to you the nobelprize.org website, because they have done a really nice job of explaining the science of all the Nobel Prizes for the general public. So thank you for coming. I'd be happy to have questions if we have a few minutes left. Thank you very much.
Thank you, Dr. Mather. So we definitely have time for questions. I'm going to bring the microphone around, so please wait till the microphone comes to you and then ask your question with the microphone.
Yeah, hi. When you said the universe is infinite, what does that mean? Does that mean that space is infinite, that mass is infinite, that energy is infinite? What exactly is infinite?
Okay, well, what does infinity mean for the universe? What people usually mean is that there's no edge. And if you imagine that you could keep on going, you just would keep on going. You would not come to a last anything. You would not come to the edge of material. You would not come to the edge of the atoms. You would not come to the end of the energy. So it's almost like the number scale that we have. You would never come to the last number. If you just keep on adding 1 to the number you have, you can never get to the last one. So we imagine that space is like that too. We can't prove it. And you can't. Anyway, with mathematics, you can prove stuff. With observation, you can only get so far.
Hi. I was wondering, what is your favorite candidate for dark matter?
Well, do I get to vote?
You only get 1 vote.
Yeah. Well, I think one of the most popular things people are hunting for, because we have a chance to actually detect it if it happens, is there's a thing called a WIMP, a weakly interacting massive particle. So it's like a big brother of a neutrino. Neutrinos we know exist. And if there are particles like them, only massive, we can calculate what they ought to do. And so in that case, we should be able to try detecting them with something in the lab. So that's a very popular topic, and people here are working on it, and people in many other labs are working on it. So far, I've not yet heard an announcement or a claim of a discovery, but we keep getting better at it. So one of these days, you might hear that at least some of the dark matter has been identified. So I don't know. We'll see. That's my vote.
You showed a very nice simulation of a collision between Andromeda and the Milky Way galaxies. Would you happen to know what the total time scale on that was?
Oh, the part that you see there, well, Well, think about how long does it take for the Milky Way to rotate. Our distance from the center, it's a couple of 100 million years to go around. So that picture is representing several orbits of the sun around the center. So it's like 1 billion years to be represented in that collision. I don't actually know, I just made that up, but
When in doubt,
that's how
say
you would
another.
get roughly the
Okay, we have
scale.
a question up in the front.
Hi, this may be a strange question, but I'm not understanding what you mean when you talk about the accelerating universe.
Oh, okay. Yeah, I didn't explain that. So what astronomers have seen is that it seems not only is the universe expanding, but it's getting faster and faster all the time, which is a huge surprise because we were so sure that the gravitation pulling things back would slow things down. So what it means is you look at things that are far away and they're too far away. So compared with what we thought they should be. So that's how it was found. So the most distant objects we found are like 20% fainter than they should be, maybe 10% farther away than we thought they were. Hint that something's the matter with our old picture. That's maybe not a big effect, but we think it's true. So unknown what really makes that happen. Going faster and faster every year, which means if you wait a long time, it'll empty out. And we'll be the only galaxy that we know of after a while, and then after our own Milky Way, all the stars die, then we'll think there is nothing else.
You had over here, you had a diagram there showing that you're going to test the alignment procedure for the mirror, the primary mirror. Launching anything into space is a very bumpy business. Are you going to be able to rattle the thing around first before you test it to make sure it's really durable?
Oh, you bet. We have shakers you wouldn't believe. At Goddard, we already have a 35,000-pound shaker. It's like a giant loudspeaker, only you can make it shake harder. And so we're getting a bigger one. So this is standard in the space business. Everything has to be shaken because you pretty darn well know it's going to have a pretty nasty ride, and you better beat it. So you're very much happier if you break it on the ground and fix it than if you launch it and then break it. So we do that one. We also have acoustic tests. We put the loudest necessary sound to simulate being close to the rocket engine. So we do all that. We try hitting it radio waves, radar waves, everything that could go wrong, we try that. And usually we're okay. But once in a while we do break something and we have to fix it before we launch. Good question. Yeah.
Hi. I asked Marcia Ricci once, who was a PI on NIRCam, if she thought that the entire sky was represented in the Hubble Deep Field images. And I was wondering and she said, yeah, probably. Do you agree with that?
Yeah, I agree exactly. Yeah, probably. And the reason that we say yeah, probably is that we've studied a lot of sky, and when we take similar pictures in different directions, they all come out roughly the same. But when you haven't looked, you haven't looked. So there's a chance that something is oddball in some direction, but it's seeming unlikely. So eventually, we're building a telescope called the LSST, a Large Synoptic Survey Telescope. It's going to watch the entire sky every 3 nights, as seen, I guess, from Arizona. And so not only will we survey the whole sky with extreme sensitivity, we'll also look for things that change every night. So we're expecting a lot to change. So it'll be a very exciting time. So that'll be a different kind of surprise.
Is there a possibility of a multiverse, and how would you prove or disprove it?
Everybody asks me that question. Mathematics says that it is that possibility. In fact, you can work out in considerable detail what such a thing would mean. As far as I know, there's no prediction yet for how you would know, which means it's purely math at the moment. So ask again in 100 years, 1,000 years, we might have a different answer. But this is one of those more and more difficult questions. So I'm sorry I can't answer that one any better.
Near the beginning of the talk, you mentioned that the stuff that we are made out of not only came from a supernova, but that it was blown out of our Milky Way galaxy. You didn't say Milky Way, but said
Yeah.
galaxy. Is that I imagined from all my reading that the stuff that we are made of always resided in our galaxy. It got blown up and it was condensed inside the galaxy again. What is the story on it being blown out of the galaxy and how did it get back in again?
Okay, well, the idea would be that the supernova, when it explodes, it goes so much energy that it expels material at immense speeds that it's got enough to escape. So it'll go out and it'll slow down, it'll bump into some gas that's out there and finally slow down. At that point, then gravity is able to pull it back in. So it doesn't mean that all of the material went out at once, but we've got these supernova firecrackers going off and stirring up everything, and so that's our idea. Now, I guess there's enough evidence that people claim this is true, but I haven't done the work myself.
How do the 20,000 cameras work? Those tiny cameras that are taking pictures. How do they work? The shutters.
The shutters. Well, what they're made, we have 250,000 little tiny shutters, and each one is made by micro machining techniques in semiconductor labs. So it turns out each one is on a tiny thread of silicon nitride, which is a flexible material, and you just move a magnet over it. The shutters are magnetizable. So pull on them with a magnet and the bend of the little shafts that they're on. And you hold them in place with an electric field, and that keeps them open. So that's the basic thing that we had to invent. We were inspired, by the way, by these projectors that we have. The projector up there in the wall may have an array of hundreds of thousands of micro mirrors that will tilt at high speeds. And we said, gee, we'd like to have one of those, but that wouldn't work for our job. So we had to make the equivalent for our wavelength and our environment. So little tiny shutters, magnets and electric fields on tiny, tiny threads.
The earliest identifiable, characterizable state of the universe from this investigation, well, the Greek poet Hesiod said it was chaos. The Bible says it was without form and void, and a popular TV show says the whole universe was in a hot, dense state. So hot is random, but it was sort of uniformly hot. So would you characterize it as random, chaotic, uniform, well-ordered? Any of those?
I think all of those adjectives apply at different phases. A story that we like to tell these days is called inflation, which says that there was something we call a false vacuum, and that the universe was in a state of considerable order, but unstable. And as it became unstable and energy was converted from this false vacuum into what we call it a true vacuum, although it's not empty either. The energy was converted into particles, and then it became chaotic in a different way. And that also was the source of the expansion energy that started to make it start to expand. So this is a story which might be true, but we go through all possible phases from low entropy to high. We claim entropy is increasing, right? So we should be going to more and more disorder. So this is one of the secrets of the arrow of time that Stephen Hawking wrote about in his Brief History of Time. I read his book and I wasn't convinced, but nevertheless, it's about the story we have, that we go from an early universe that's more ordered to a future universe that's less ordered, and that's how come we're here.
Great. I think we've got 2 more questions. I've got people identified. Let's see where we are at that point. So.
Oh, thanks. I just had a question. The environment in which the JWST is going to operate at the Lagrange point, what sort of dangers exist in terms of small particles, like meteoric particles, in terms of affecting the mirrors and the rest of the machinery of the telescope?
Okay. Actually, we had to think about that right away at the beginning, because we are exposed to the dangers of space. Now, the Lagrange point isn't any worse than the other neighborhood over there, because particles are not accumulating there, but we will have little holes in our mirror by the end of the mission, because we are bombarded all the time by little tiny dust grains that are just in orbit around the sun. And so we know they're there, we know how many of them there are. We've even simulated in hypervelocity colliders what happens when a dust particle hits a sheet of beryllium. We know how many holes there will be in the big umbrella. all that stuff. We even had to calculate how many holes there will be in the insulation on the wires in the cables. So we are aware of it, and we certainly hope we're doing the right thing. So not a trivial matter. And there was one more question. Do we have?
Hi. So this is related to the last question. Why was the L2 point chosen for the telescope to operate at? It seems kind of far.
Yeah, the L2 point is far. It is the boundary between Earth orbit and solar orbit. So it is the place where you can go. It's the only place you can go that we know of where you can sort of hang overhead and not go away from the Earth, not get farther away, and also not go between the sun and the Earth where we would never be able to keep the telescope cold. If you're in low Earth orbit, you're always going around very quickly, and the sun and the Earth can shine on both sides of your telescope sometimes, so you can't build your umbrella. If you go too far out, then sure you can build your one-sided umbrella, but you escape from the Earth, and you can't talk to the observatory very well. So this is the boundary. All these Lagrange points are boundaries between Earth orbit and escape. So that's why we chose it. It's the unique point that we know of where we can do that. So thanks again for coming. It's been a pleasure talking with you and with your questions.
Dr. John Mather one more time.